Next, we have Angus Thies. He is attending University of California, San Diego, where he is pursuing a degree in marine biology with a minor in environmental studies. He has been working here in Newport with the EPA this summer, and one of Angus's goals, that was somewhat similar to Stephanie's, was to cook something new each week to broaden his cooking skills.
Yeah,
so
I set off the fire alarm.
Yeah, you had an extensive
batteries,
dorm
actually.
kitchen, but
Yeah. Okay. So, like Haley said, my name is Angus Thies, and I've been working at the US EPA this summer. And today I'm going to be talking about environmental reservoirs of fecal indicator bacteria. Yay! Okay. So in the United States, microbial contaminants are a big problem, especially fecal contaminants in bodies of recreational water. Some familiar examples you guys have probably heard of are salmonella and pathogenic E. coli. So, as you can imagine, there are a lot of ways these pathogens could make their way into waters. These include wastewater, treated sewage, and even from agricultural runoff. So, testing for these pathogens is a big issue, and it's an important issue. But there is a big problem with it. When we go out and test for these pathogens, we don't know what's there. So we get a lot of false positives if we directly try to culture these bacteria. So the solution has been to use a group of microbes called fecal indicator bacteria. Fecal indicator bacteria, or FIB, are non-pathogenic microbes that are closely associated with these pathogens. As such, they're used to set recreational water quality limits in the United States. So in this presentation, we're going to be talking about two specific groups. The first is fecal coliform, or FC. This is a group of microbes that's used to regulate water quality in areas with shellfish growing operations, such as Tillamook Bay. The second is enterococci, or ENT. This is used to regulate outside of these areas in marine and brackish waters. So in Tillamook Bay, there's a very long history of FIB exceeding regulatory limits. And that's a really big problem there, because as I said, there's a shellfish aquaculture industry. When these levels exceed regulatory limits, there's a mandated temporary closure of a harvesting period for these operations because shellfish are bioaccumulators of pathogens. So, this study sought to address the prevalence of fecal indicator bacteria in Tillamook Bay and to assess whether there are environmental reservoirs of FIB in the water, and if these reservoirs are actually contributing FIB back into the water column. So to do this, we looked at three specific goals. The first was to address the spatial variability of FIB within Tillamook Bay itself. The second was to look at two environmental reservoirs, eelgrass and sediment, to see if they actually do harbor these pathogens. And three, we were going to compare the differences of eelgrass and sediment between two different bays, Tillamook and Yaquina. So to address these goals, we sampled water, sediment, and eelgrass from 11 different locations in the two bays. From all of our samples, we quantified FIB using IDEX techniques. We took sediment samples and looked at their moisture content and organic matter content. For eelgrass, we did something special. We separated out the microbes that were on the plants into those that were loosely attached to the leaves and those that were tightly attached to the leaves. Finally, we also looked at microbial DNA from all of our samples and saved that for source tracking in the future. So here are our main results. As you can see, enterococci levels are displayed on the left and fecal coliform on the right. Red box plots represent data from Tillamook Bay and blue from Yaquina. Along the x-axis, we have our sampling categories, starting with microbes loosely attached to eelgrass, tightly attached to eelgrass, microbes in sediment, and microbes in the water column. Finally, there are two little dashed lines going across the plots. This might be a little hard to see, but they go across right about here and right about here. And those represent the regulatory limits for fecal indicator bacteria. So, just looking at these, we have some general results. The first is that in both bays, enterococci levels were very elevated when attached to eelgrass, and actually they were above regulatory limits. Second is that microbes that were tightly attached to eelgrass were not mainly FIB, and they weren't even close to regulatory limits. And finally, sediment FIB levels were generally pretty variable, but they were also usually below regulatory limits. So when all of this is taken into consideration, there are two main conclusions that are important to share. The first is that sediment and water column FIB levels weren't even close to being correlated. But organic matter content in sediment and enterococcity levels in sediment were very closely correlated significantly, positively, This indicates that sediments with a high organic matter content could increase the survivability of FIB in this sediment. This could lead to a decoupling of levels in the water column and actually in the sediment. And secondly, and the result that I actually find most important, is that a high fraction of the FIB that we found on eelgrass, about 92% of enterococcity and 99% of fecal coliform that was on eelgrass, was loosely attached to the leaves. This is also very important because it indicates that agitation of the leaves could resuspend these microbes and their associated pathogens back into the water column and allow them to retravel to the bay. We don't know if these populations of FIB on the leaves are naturalized, as in they've regrown, or if they're actually resulting from fecal contamination. Hopefully, using microbial source tracking with the DNA we've collected, we'll be able to get some idea of this in the future. So before I end, I would just like to thank Oregon Sea Grant and the US EPA for giving me this opportunity. And I'd really like to thank my two mentors, Amy Zimmerfaust, who unfortunately can't be here today, but also Cheryl Brown. Thank you guys very much.
So what did you do to this eelgrass to get loosely attached FIB off of it? Or tightly attached? What was the difference?
So we use the very scientific and widely used method of putting it in a bag and shaking it. So it's a pretty simple system, but it's actually apparently the standard in the industry based on a literature review is to take a known weight of eelgrass, put it in a Ziploc bag, and shake it around with milky water. Pour off that first rinse, and that's your loosely attached fraction, and then reprocess it again with the same shaking, same volume, and then remove that second volume and look at what's still on the plant. You can also massage it around, try to get as much off as you can. But generally, just based on the data, the vast majority was loosely attached to the plant. So it was pretty impressive how easily that would come off and become resuspended. All right. Thank you guys very much.